Time for some examples of naming alkanes, and as we go along we'll be looking at a few examples of functional group identifications. All right, so IUPAC names are the ones that we will focus on in this course, and there are some others, but most of the time we won't be using them so often. For now, we're going to focus on understanding the IUPAC system. The first thing is to find the longest continuous carbon chain. On the example on the left, I just drew a line through the longest chain, which in this view apparently has 5 carbons. The parent compound name is therefore that which correlates to 5 carbons, or pentane. Pentane then has extra substituents on it in this example, and we'll have to name and locate them on this main chain. We want to number the main chain to give the lowest numbers to the substituents. We could either start with carbon 1 here, or we can put carbon 1 on the other end. In this case, the answer that gives us the lowest numbers for our 2 substituents, one being here and the other here, would be putting carbon 1 on this end, not the other one. So that puts the first substituent on carbon 2 and the second one on carbon 3. And identifying the substituents, again, this is something you'll need to get comfortable with. The more you do, the more obvious it is. This one is a methyl group, carbon with 3 hydrogens, and the second one is also a methyl group. So we will put that description in front of the pentane, and so methyl, but there's more than one. So how do you describe it when there's more than one? Simply enough, you put a prefix on there, and so the prefix for 2 is di. Are we done? No, because there's more than one place that those methyl groups could be located on this chain, and they would still be valid structures. So we have to list a number for each substituent. We'll put that in the front. 2, 3, hyphen, dimethylpentane. All the rest is all one word. I didn't leave the space suitably to make it all smooth, but that's the way you'd want to type it. Okay, second example on this page. Step number 1, find the longest continuous carbon chain. That means you drag your pencil, your finger, whatever, through it without retracing. And this one is laid out, from what I see, pretty straight, or across horizontally, if you will. Straight is a funny way of saying things because they're all kinky. The geometry of carbon in these compounds is such that 109-degree angles leave nearly nothing straight. So if you can count, I think I can count 1, 2, 3, 4, 5, 6. So the longest chain in this case is 6, being the prefix for that type of alkane would be hexane. And then we have to identify and locate the other substituents on the main chain. It helps to circle them so you don't overlook anything. And so that needs to be described, another CH3 group, and this one over here needs to be described, 2 of them. Well, guess what? It's the same idea as the one on the left. So this is 2 methyl groups, so we call it dimethylhexane. Now, before we finish with the name, apparently we'll have to describe where those substituents are located. If you want to put numbers on the main chain, you're going to do it such that you give the lowest numbers to the substituents that are possible. And you either put carbon 1 on the right or carbon 1 on the left. In this case, if you look at it, that would put one of these substituents on carbon 2 and the other one on 3, 4, 5. But if you count the other direction, you get the same thing. And so this compound is symmetrical. It doesn't matter which way you number it, they'll come out the same. And so the numbers for the 2 substituents both have to be included. I could have put it on the same line, and I just didn't. 2, 5, dimethylhexane. Okay, another example of understanding structures, functional groups, and names. One way of working with things is making condensed formulas. I don't always like them, but there are times when you'll need to work with them. So let's talk this one through and see what we have. Again, we have to figure out what we're looking at. The longest chain in this structure appears to be more or less horizontal, and then you'll have 2 extra groups at the top. Looks like CH3 groups twice. And so to make a condensed formula, what would you do? So one of the ways to do that is to put CH3 and then a line, but you don't but we can draw a line to make it at least not too cryptic, too confusing. And so one methyl group here, and you could put the second one up above, but I'm going to just draw the second one below because it's less crowded. It means the same thing. And so there's two methyl groups, and then no remaining hydrogens on that carbon, followed by a CH2 group and another CH3. All right, so there's a condensed structure for it. What will we do next? There's no oxygen in this compound. The red designation up there is just in case you run into one. So longest chain is apparently across here, as I mentioned, and that would be 4 carbons. So the last name for this structure is going to be, according to the functional group, well, let's see what functional group is present. It's all carbon and hydrogen with no multiple bonds, so that would be an alkane. And with 4 as your longest chain, it better be butane. And so what do we have on the butane? Well, guess what? It seems to be a common theme that you're going to have a couple of methyl groups in front of this name. And so we'll have to decide what we want to do about describing their locations. I think that if you look at what I have shown here, by chance we picked a number from the left because we sort of think that way. And in this case, it works out with lowest numbers to put those on carbon 2. If you went the other way, it'd be carbon 3. So this time it's going to be 2, 2 dimethyl butane. 3, 3 might be correct, but it might look correct, but the best answer, the IUPAC name gives lowest numbers to the compound. Okay, more practice. Functional groups, we're not going to name these ones yet because these are more complex than we've discussed so far. Chances are you'll need to have your functional groups table handy to work on these, but know that you really need to get acquainted with these. The more examples, the better. One hint that you have a functional group is when there's some atom that's not carbon. So there is one that's oxygen in a double bond. Here is another group that has an oxygen between 2 carbons. We'll need to identify that. And then here's something that's not just single bonds, so we will want to identify that as well. Again, you can't find anything else, you'll call it an alkane, but when there's other things, we'll describe them for certain. Okay, so example A on the left, I've circled 3 different things. Hopefully you recognize these gradually. The first one is the easiest one, or at least I think it is. It's called an alkene whenever you have a double bond. Not a big deal. It's what we're going to see in the next chapter. It's going to be alkenes. The other ones take more practice. The oxygens singly bonded to 2 neighboring carbons that have nothing else besides just ordinary hydrogens on them. That one is described as an ether. And then the carbon with a double bond oxygen on the right, that takes more practice because there are a number of things on our functional group chart that have that. It depends on what's next to it. In this case, it's between 2 carbons, and neither of those carbons have anything besides hydrogen on them. If there were an oxygen or a nitrogen, then it would become something else more interesting. Or if there was only a hydrogen there, then it might be something else to consider. But this one's just between 2 carbons, so this one is described as a ketone. Fair enough. The compound on the right, again, look for things that are interesting, namely something besides just single bonds, something not just carbon and hydrogen. Here's a double bond on the left side. On the top, we have a blue atom with something, those are hydrogens attached. Blue is going to represent nitrogen. And oxygens, I guess I didn't specifically say that just now, but oxygens are red. And so this compound has oxygen, 2 oxygens on the same carbon. That becomes important, so you'll get familiar with this the more you see. But this one has a double bond oxygen on the carbon that also has oxygen with hydrogen. Now we need to take a look at that functional group chart and see what applies. All right, start from the left. Well, guess what? A carbon double bonded to another carbon is exactly what we saw over there in the first example. Again, that's an alkene. No big deal. That's the easy one, I think. It should be. Get familiar. The one on the top with the nitrogen with only singly bonded atoms anywhere near it, that is the one that starts with A. Many of these start with A, beware. Is called the amine. And on the one to the right with C double bond O and OH on the same carbon that had the double bond O, that one is going to take some practice. but that one's called a carboxylic acid. As we see more examples, eventually you'll realize that a carboxylic acid is sometimes shown with a condensed formula that is represented as COOH. It feels a little awkward for a while, but as you stare at it and think about it, it should make sense that that COOH is the same thing as what we show with the ball and stick diagram. Okay, more examples. Let's see. We could make line drawings and find functional groups. Let's see what we can do with that. All right, so the line drawings aren't too bad. What you need to know is when you have a cyclo compound, we do not show the carbons. We just show corners. And so for the first one, it has a cyclic structure with 5 carbon atoms in the ring, and so we'll get good at drawing some kind of a polygon. In this case, with 5, we call it a pentagon. And it's actually a lot simpler than you first think. It has a double bond between 2 of the carbons, and then a carbon adjacent to that, you got to think about it, is going to have a double bonded oxygen. You do not have to show any hydrogens. It feels really crazy at first, but that's all you have to show. So, functional groups, well, the double bond is between carbons is one thing, and double bond to an oxygen is something else. And so the double bond between 2 carbons, we've seen this example now and again. This is the alkene, and the double bond to oxygen is a ketone again, in this case because there's nothing else besides carbon and hydrogens on the adjacent side, adjacent to the carbon double bond oxygen. All right, the one on the right, let's see. Blue is nitrogen, right. And we're going to draw this structure in a line drawing, and with cyclostructures, again, it's just going to be polygons. So if you count your carbons here, I see 6, and so draw a hexagon. Artistic skills, arbitrary, trust me. We all do the best we can, but they don't have to be wonderful. Master in chemistry is very tolerant. And one side, we have a double bond up there between the 2 carbons. One next to it has a single bond, and then the one adjacent, one step over, if you will, has another double bond. And then this carbon adjacent to it doesn't have anything, and then, or nothing besides hydrogens. And then one carbon away from the top double bond has a nitrogen with 2 hydrogens on it, so we'll just write NH2. And then in addition, it has something else there, or would. It's methyl, CH3. I'm hoping you're getting familiar with that the more times you see it. All right, so now we have to identify some functional groups. Hopefully, you're getting acquainted with these, and you'll recognize that the double bond here and here in this structure are only alkene. You do not have an aromatic compound until it's a 6-sided ring with alternating single and multiple bonds. There is one side that doesn't have that, and so these are only alkenes in this structure, and they're also shown down below as well. And my line drawing. The only other part of this compound that's not alkane then is the NH2 group, and that is one of those words starts with A. Oh yeah, lots of them. And this one is the ordinary amine because the carbons next to it don't have any double bond O. If it did, then you'd have to be looking for something else. So that is also a simple one to remember if you get practice with it. Please do. Please do. All right, more examples. There are lots of them. Let's do another name. Let's see. I believe I want to pause and tell you that we might have done one similar to this. Let's think. Okay, similar but not quite the same. So, many examples. Let's see what we know. I would like to do this one without taking too long because it's quite similar to the one we saw before. Longest chain across the bottom doesn't look very tricky. On that, we have 2 groups of CH3. Those are both methyl. So if the longest chain is written across the bottom, I think starting from the left gives you lowest numbers again. Doesn't always, but it does in this example. And the longest chain of 5, the last name of the compound, I hope you're catching up and getting there with me, is going to be pentane. And 2 of those CH3 groups on the second carbon will be methyl. And so we put methyl in front of the word pentane. And to describe how many there are, we use the prefix and dimethyl. And again, I leave enough room, that happens every time. And so there'll be 2, comma, 2 hyphen dimethylpentane for that one. Not so bad. Very similar to the other one, but a little bit different. All right, one more on the right here. What shall we do? Longest chain. Let's work our way across. I'm going to draw this one going up and down, kind of zigzag. But let's see if we go down. Does that give you anything different from another choice? Actually, you could go up or down at the right here and you get the same thing. The longest chain looks like 1, 2, 3, 4, 5. Oh, pentane again. There's a lot of examples of pentane sometimes. And it makes you don't, so you don't have to count with more than one hand. How about that? And so on that pentane, we have some extra substituents that need to be noted. Again, if you find your longest chain in the circle, what's left? It helps you to remember how many things got to go in the name. Oh, guess what? This time we got 3 other things, and they're all the same thing. And so, well, guess what? If this is methyl, the favorite thing we tend to have in these examples, but for right now it's the easy ones. We like easy for now. We'll see more gradually. And so how many of them there are is reflected with a prefix. This time the prefix for 3 is tri, so trimethylpentane. And now we have to describe what number they're on. Are we going to describe them as being on 3 twice and 4? Or is there a way to do lower numbers? Guess what? There actually are lower numbers. So what if we start on this end? Then we have 1 and 2 and then 3. And so we have 2 and 3. So 2 and 3 instead of 3 and 4. So that would be preferred. So again, we give it, every substituent gets a number, so it's 2, comma, 3, comma, 3 dash trimethylpentane. Wow, how about that? All right, now here's another one or two to try. Get an idea how these things work. What do we understand about straight chains and what are branched? Well, we have to look at these. Is A branched, B straight chain, B branched, A straight chain, both branched, both straight chain. Take a look at this, see if you can figure it out. Hopefully you've seen these compounds because we just looked at them, didn't we? And so if you have more than something you can draw your longest chain through, and in fact we did, whoops, I didn't finish my line, then there are branches on both of these compounds. So both of these things are branched compounds. Oh, let's see. How about something that we haven't seen? That one we have seen. Do another one. I keep figuring out. Forget when things have been duplicated. How about let's do this one. Let's do a condensed formula for these things and identify the functional groups present. All right, so we have, what does condensed mean? So it means that we're going to write CH3 instead of drawing carbons with lines for hydrogens. We'll simplify things that way. And that's this first carbon. The second carbon here is just a carbon that has what? 2 methyls on it. Well, here's another way of condensing. We can also list this as CH3, and I'm not trying to make that smaller. I'm just doing poor drawing here with my finger on a touchpad. 2 of those on the same carbon, followed by CH2. I'm just working left to right, and then on the right is another CH3. Guess what? I'll bet that you would prefer to see it drawn out because it's not as clear to you. But these 2 CH3 groups on that second carbon can be shown in a parenthesis after that carbon to which they're attached. You have to stare at it for a little bit if you don't see it right away, but every carbon still has 4 bonds. What functional groups are present in that molecule? This is only an alkane. And I bet we've actually drawn something or named something just about the same as already, haven't we? That looks to me like 2,2-dimethylbutane. Pretty sure we did that already. Okay, the one on the right. What shall we do with that one? We're going to figure out how to do a condensed formula and make sure we understand how they work. I'm just going to work from left to right to do that because it's the easiest, so you don't get lost. It's easier to write that direction, I think. And you can do what you want, but this is one way to get there. So we'll start on this end with this CH3. Next to that is a carbon that has both a hydrogen and another CH3 group on it. So what do? Sometimes we're going to see it drawn like this with a parenthesis at CH3, sometimes we're not. And so the CH3 can be shown separately here. I'm writing over the diagram a little bit. Apologies. But this time I'm not going to condense it the way I did on the left. Let's just draw a bond to that extra carbon, extra CH3 group. That's fine. And then following after that, we have another CH to which an OH group is attached. And so we can either put it in the line with the other structure, but we can write it down below as well. It's a little easier to work with that way. Most of you prefer to see it more written out. And then on the end, that's this guy. And then on the end is another CH3 group. So, functional groups present. Most of this has just carbon and hydrogen single bonds, again, alkane. And there is one other portion to this molecule that's interesting. And guess what? It's an OH group. I'm hoping most of you are catching on to this one, but this one is simple compared to other things. It is the alcohol. All right. And so I think that's about all I'm going to show you today. How about one more functional group practice to look at here? Yeah, why not? All right, so these things are things that you might have heard of somewhere. Acetaminophen is in Tylenol, and it has some things that are not black atoms, so there must be something interesting. It's got a red one over there. That means it's oxygen with hydrogen, right? And then in the middle it has this ring. That ring is a little bit deceptive. I'll have to explain that. And this carbon on the right with an oxygen on it also needs some explaining. Well, why do I say that? Carbon has 4 bonds, but they're not all represented in these particular diagrams. So one has to infer something. This carbon that I've just labeled here has 1 bond to the oxygen, 1 bond to 2 carbon neighbors. That means it still needs a bond. A second bond, a double bond, is not shown. It's only inferred. And so I'm going to have to complete this structure with some more bonds. Each of these carbons only shows 3 bonds. And so to make more sense of the whole thing, we'll write some more in. So there should be some alternating multiple bonds here in order for the structure to be complete. Carbon will have 4 bonds. A ball and stick model might not show all the bonds, but it will show the atoms. Makes things more interesting. Again, there's another carbon over here on the right with the oxygen on it that doesn't show enough bonds because it's got 1 to nitrogen at the left, 1 to carbon at the right, 1 to oxygen below. That's only 3. So where else can you put another bond? If it were to a neighboring carbon, it should be shown, but this oxygen also needs 2 bonds, and so the double bond belongs between the carbon and the oxygen. Most of the time we won't make you infer that, but it's worth explaining today. So as it turns out, this C double bond O next to the nitrogen makes that all one functional group. We call that an amide, and we're not always as proficient with them, so it's good to run into them once in a while. On the end is just a CH3 group that's a methyl, but that's not a functional group. The one on the very left end is the OH group, also known as an alcohol. Most of you catch on to that one fairly readily. And then now that I've added the extra bonds in that 6 carbon ring in the middle, now we have something that constitutes a different functional group that hasn't showed up in the examples in this recording. That 6 carbon ring with alternating single and multiple bonds is called the aromatic ring, an aromatic functional group. Voila, exciting. Now, the other one on the right is called aspartame. It's an artificial sweetener. Maybe you've heard of that. And so this one is a different one. It's not ball and stick. Perhaps you prefer that, actually. Again, it has a 6-sided ring with alternating bonds. Guess what? There you have another aromatic ring. You also have a few other things to look at that might be similar. And so just like we had a nitrogen with a carbon neighboring to a double bond oxygen below, that's what we see up here too. And so that is also an amide. We'll try not to make this too messy. There are a few other things to look at. There's a C double bond O with carbon next to it. Oxygen and carbon next to it. There is a COOH that I mentioned on a previous slide. There is an NH2. Oh boy, 3 more things to mention. So the NH2 is the easiest of them, I hope. That's just the amine. So nitrogen with bonds to hydrogens and or carbons, got to have at least one carbon, is an amine. The COOH is one we saw a little bit ago. It's called the carboxylic acid, and that is the short abbreviation for it, but you're not going to necessarily like it. Whoops. Oh boy, I didn't even have to write this, did I? But it's much easier to write COOH than to draw the whole thing out. So take that, try that on for size. We'll work with them a lot more by the time we get to chapter 17. And then the one on the right. Look on your functional group chart. I hope you're looking these up as we go. And C double bond O with oxygen is going to be in the functional group that haven't showed up in this recording yet. This is one that takes some practice to make sure you're spelling it and thinking it correctly. This is the ester. So C double bond O with an oxygen and a carbon next to it becomes an ester. All right, wow, what a bunch of new things to practice, functional groups and names. I hope you find that helpful. Good luck on your homework. See you in class.